Hello. Let me now go back to the sum to infinity sequence that I talked about in an earlier video. We'll see how we can apply this formula for the sum of a GP to sum a GP to infinity. If you remember the sequence I'm referring to, this is what it looks like. Half plus quarter plus 1/8 plus 1/16 and so on. You get the next term by multiplying the previous term by half. So times half you get quarter, times half you get 1/8, times half you get 1/6, and so on. Now what I like to do is to keep adding more and more terms forever. And as I explained in that earlier video, the final answer, or rather the answer just gets closer and closer and closer to 1. So I'm going to add up an infinite number of terms. So let's see how we can apply the formula that we've just seen for the sum to n terms of a GP. Now I can think, now this is a GP, because if I think of this as the first term A, then each time I multiply by r by a half to get the next term. So the common ratio r is equal to half. Okay, so that's AR, that's AR squared, that's AR cubed, and so on. And we want to keep adding on and on forever. Now if you remember the symbol for the sum to n terms is Sn. In this case, since there is an infinite number of terms, my n is actually infinity. Now an infinity, the way to write infinity is with what looks like a horizontal figure of 8. So if you imagine taking this number 8 and rotating it 90 degrees, that's just what this symbol is. And this symbol means infinity. Okay, so that symbol means infinity. Okay, so now then let's recall the formula. Sn is equal to a 1 minus r n over 1 minus r. So how would we apply this to this case, to a sum to infinity? Now if the number of terms goes to infinity, that means I'm going to have an infinity over there, r to the power of infinity. Meaning, if you like, imagine r to a power that is extremely large. If I put a number r to the power of a number that's extremely large, shouldn't I get an answer that's also extremely large? Yeah, you know, like if I do 3 to the power of 2, or 3 to the power of 10, or 3 to the power of 100, if I keep increasing the power, surely my answer should get bigger and bigger. Wouldn't this happen to the r to the power of n if n goes to infinity? Well, the answer is yes, if r is 3, for example. But in this case, r is half. Why does that make a difference? Well, okay, if you look at half, if I take half and then I take half squared. The half squared is 1/4. I actually get a smaller number and not a bigger number. If I take half cubed, I get 1/8, which is even smaller. So what this means is that if r is a fraction, if r is a number that's smaller than 1, then when the power gets big, the number actually gets smaller and smaller. So what happens if the power goes to infinity? What if the power is a number that's extremely large? Well, since as you can see from this trend here, since r to some power just gets smaller and smaller, we might expect that when the power goes to infinity, this should just go to 0. And indeed, that's what happens. If r is a number that is smaller than 1, then when n goes to infinity, r to the power of n goes to 0 if r is less than 1. Okay. Now let me be more precise here. Because if r is a negative number, let's say if r is negative 2, then I'm going to have negative 2 to some power. Then if the power gets very big, the power of negative 2 would also get very big. So r must not just be less than 1. It's the numerical value of r that's less than 1. That means it's a number for r apart from the sign. So that means that r should be more than -1. Okay, so the numerical value of r, or I can use this sign with the 2 stroke, means that I just take the numerical value and ignore the minus sign. So the numerical value of r should be less than 1 for this to be true. For r to the power of n to go to 0 when n goes to infinity. So it can be some fraction whose numerical value is less than 1. So finally, I can write down now the formula for the sum to infinity. So s to infinity is a, and then that's 1 minus 0 over 1 minus r, because r to the power of n would go to 0. Okay, and it is important to remember that for this to be true, the magnitude of r must be less than 1. The numerical value of r must be less than 1. Now I can write this a little bit more simply. That looks a bit awkward. That's just 1 minus 0, which is 1 times a, which is a. So let me just write this as a over 1 minus r. So now I have a formula for the sum to infinity. If we know from that earlier video that the sum of this sequence to infinity is 1. Let's see if I can get the same answer using this formula. So how shall I apply this formula? If I want to apply the formula to this sequence, then okay, a here is half. So let me put in half down here over 1 minus, and r here is also half. Okay, the common ratio is half. So 1 over half over 1 minus half, which is just 1, right? 1 minus half is half, and half over half is 1, which is the same as this. So therefore this formula works for this. Okay, and this formula is useful because even if it's not this particular sequence, I can imagine another sequence that goes to infinity. Okay, maybe starting from 1/3 instead of half, and starting with using some other common ratio that's not half, maybe 1/4. So as long as the numerical value of r is less than 1, then for any value of r and any starting number for the sequence, I can always use this formula to find the sum to infinity.